All right, good morning. So today we're going to talk about P. Last time, actually the last couple lectures, we talked about the time hierarchy theorem. So I posted on Piazza some stuff that you should read, just following up on that. Let me say a few things. So the time hierarchy theorem, one thing that it implies is that there are languages that you can decide in, say, exponential time, but that are not in P. So there are definitely some problems that are not solvable in polynomial time, and not for like a ridiculous reason like they're not solvable at all. You can solve them given enough time. They're just not solvable in polynomial time. And last time we spent a lot of time, we fixed a time-bound n cubed, and then by working hard we found a language that couldn't be solved in a little bit less time, like n squared time, but it could be solved in a little bit more time, like n to the 8th time. And you could do the same proof with a time-bound, let's say 2 to the n, and that's how you would prove this theorem. So in fact, this language called bounded accepts sub 2 to the n, which is the language of all Turing machines and words, W, such that this Turing machine code run on this word halts within at most 2 to the length of W steps. This is an example of such a language. Okay, and that's one explicit example of such a language. If you just want this fact, you can just use the time hierarchy theorem and plug in T of n equals 2 to the n, say. So this particular language is an example of one which is not in P. In fact, it's not in an amount of time that's anything a little bit less than 2 to the n. So for example, it's even not in time, 1.99 to the n. On the other hand, you can solve it in like a little bit more than 2 to the n time. So if you use the universal Turing machine that we studied last time, then maybe this one you can show is in time 2 to the n times a little bit, maybe times n to the 5th or something. Okay, which is a subset, if you want, of time 2.01 to the n. Okay, so several times I'm going to write relationships between these classes that look like this. So it's good practice. If you have any questions about what this means or why it's true, please ask. OK. So just before we get to P, let me make one definition. It'll be the definition of a new complexity class. So we've studied two complexity classes before, or two kinds of complexity classes. These time classes, where you give it a specific time bound. And P, the polynomial time, is anything that, all the languages that can be solved in some polynomial running time. And I'm going to make an analogous definition for exponential time. So it's usually written exp. This is a class of all the languages that can be solved in exponential time. So what does that mean? It's all the languages that are in some time class of the form 2 to the n to the k. Okay, or languages decidable in, I might write 2 to the poly n time. Okay, so this is a very big class, all the languages solvable in exponential time. This bounded accepts is in this class. So if I want to show that this bounded accepts is in exp, what k would I need to put here? Yeah? K equals 1 does not quite work. So I mean, k equals 1 is asking is it in time 2 to the n, which means it should have running time order of 2 to the n. And this we don't know. This is a little bit bigger than 2 to the n, so we don't know if it's in this running time. Yeah?
It's definitely within k equals 2.
Yeah. But k equals 2 would be fine. So if I looked at n squared, and this is definitely big O of this. 2 to the n squared is much, much bigger than 2 to the n times n to the 5th. Because the log of this is about, the log of this is order log n. The log of this is order n squared. It's n squared. OK, so right, so this is a very big class. Of course, P is a subset of X. Remember, these are classes of languages. So every language that you can solve in polynomial time, that same Turing machine that proves it also shows that it can be solved in exponential time. Of course, that means it can be solved in at most exponential time. Yeah, but actually, they're not equal. They're provably not equal by this time hierarchy theorem. So for example, this is an example of a language which is in X, but it's not in P. OK, so that's kind of nice. I mean, yeah, last time, at first I said it would be great to find any language that's not in P. And then I said, well, let's try to find a language that is not in P, but it's at least decidable. And you can get that by diagonalization. And then I said, well, let's try to find a language that's not defined in a weird way by a diagonalizing Turing machine, but that's at least sort of natural. So this is an example of a kind of natural problem that's not in P, even though it's in exponential time. But even this is still not the most natural problem in the world. I mean, it's OK, but most people don't go around stressing about the problem of simulate this Turing machine on this word for 2 to the n steps and see what happens. So it would be great to get even a truly natural computer science problem that you might want to solve that you can solve in exponential time, but you cannot solve in polynomial time. Well, actually, in some ways, that would be bad, right? I mean, the dream is that every problem that you care about can be solved in polynomial time. It's just not true sometimes. So at least it's good to know it when it's not true, to be able to prove such statements. And just to get back to something I said in the first lecture, I mean, one goal of computer science even, or especially computer science theory, is just for every natural problem or nice problem that you might actually want to solve, find the fastest algorithm for it. And this, of course, has 2 parts. One, equally important part. One part is finding a fast algorithm. It's the remit of algorithm study. And the other part is proving that there's no faster algorithm. And that's hopefully the remit of complexity theory. So let's talk about these nice problems, or what are the computer science problems that we actually end up caring about and trying to solve with algorithms. So we're going to talk about this in a lot more detail when we start talking about NP completeness. But here's common features of some problems that we care about. They're often they're kind of like puzzles. I'll give examples in a second with exponentially many candidate solutions. If you're solving a jigsaw puzzle with n pieces, there's exponentially many different ways you can put them together, and only one is the correct answer. But they usually have the feature that you can recognize the correct answer when you see it. Actually, I should probably say a correct answer, because most of these problems have more than one solution. And therefore, a lot of problems, natural problems, are in exp by a brute force algorithm. A brute force algorithm, I mean, the one that just lists all the possible candidate solutions, one by one, of which there are exponentially many, and then just checks to see if it's a good solution. OK, so it's usually not too hard to show nice problems, reasonable problems are solvable in exponential time. And then the real question, that makes a big difference is, sometimes they're in P by a clever method. OK, and that's the whole heart of algorithms design, trying to figure out a smart way to cut through this haystack and find the solution, which is the needle in the haystack. OK, so today what I want to talk about is just a bunch of problems. And almost all the ones I mentioned are going to be in P, solvable in polynomial time. But I want to illustrate how they kind of fit in this framework where, if you look at just the definition of the problem, it looks like there's exponentially many things you'd have to try to find the solution. And you can solve the problem by trying exponentially many things, but there's also smarter things you can do. So I mean, later in the class, we're going to, it's a complexity class, so we're going to talk more about like problems that we don't think are solvable in P and reasons why they might not be solvable in P. But I want to spend some time assuring you that there are some great algorithms that sometimes surprisingly show that a problem that looks very challenging can be solved in polynomial time. So if you get a problem, it can be unclear whether there's like a smart way to solve it or not. Yep?
So are there any questions that are like contrived like this that have been proven to be in ESP but not in?
Yeah, there are like non-contrived questions that are provably in exponential time, but not in polynomial time. For example, like, you can define like a generalization of chess, where instead of an 8x8 board, you can have like an arbitrary size board with like, more than just the 32 pieces or however many are. And like the input is like, a potentially large like chessboard with lots of pieces. And the question is, can white win from this position? And this problem can be solved in exponential time, and you can also prove that it cannot be solved in polynomial time. OK, so maybe chess is a bit funny, but like there's other like very natural like problems. Like I can't remember some of the other ones off the top of my head. Like I'll get to it later. But yeah, there are such problems. OK. Great. So yeah, so I'll tell you 4 or 5 problems today. So the first one is one that is called, I know you know about. We'll call it, well, Sipser in his book calls it path. A lot of people call it ST path. And here's the problem. The input is 3 things. It's a graph. Well, it's the encoding of a graph, S and T, okay, where G is a graph. And S and T are vertices. And the output is yes or no. It's a decision problem. As usual, I mostly focus on yes/no problems, decision problems. Yes or no, is there a path from T, a path from S to T in G? OK, so the input's a graph. And names with 2 vertices, and you just got to know, can you get from S to T in G? And let me emphasize that when you say graph, you might ask, is it a directed graph or an undirected graph? Most of the time, actually, I consider undirected graphs. But for this problem, I definitely mean a directed graph. It's not a big deal. It's just it's potentially harder in directed graphs, but as we'll see, it's not actually harder. Now, just before I get into it, I don't want to talk about this every single time, but since we're going to be talking about algorithms and polynomial time and stuff, let me take a few seconds to talk about what does it mean, the encoding of G. There's also S and T, but let me just focus on what does it mean to take the encoding of G. Well, as you know, we should really talk about maybe in Turing machines, but like today, we're going to just talk about normal algorithms written in pseudocode. But still, you have to ask yourself some questions like, well, how do you encode a graph? There's several popular ways to do it, like the adjacency list format, or the adjacency matrix format. Right, this is where you have like a list of the vertices, and each one has a pointer to another list, which gives all its neighbors. This is where you just have a big n by n matrix, n being the number of vertices, with a 1 if there's in the uv position if there's an edge from u to v, et cetera. So one thing I want to say is, if you just care about whether or not stuff is in polynomial time or not, then it doesn't matter. That is to say, whether a certain problem involves a graph is in polynomial time or not isn't affected by whether you assume the input is in adjacency list format or adjacency matrix format. So why is that? Yeah?
Like, I mean, I feel like you can probably translate between the different formats in polynomial time.
That's right. You can transform between the different formats in polynomial time. So if you had some algorithm that solved the graph problem in polynomial time, given the adjacency matrix format, but you want to do it given this adjacency list format, well, you could just stick a little subroutine on at the beginning that took it in this format and converted it to this format. And that subroutine itself is not very hard. You can write it in pseudocode. It's polynomial time, quadratic time, or something like this. OK, so if you're just not too concerned about like very fine-grained details of the running time, just whether some problem is in P or not, then it doesn't matter. And mostly in this class, that's what we'll be like. It's not an algorithms class. So in particular, it's up to you. If you want to like when you're writing an algorithm, if you want to assume it's in this format or the other format, then that's fine. Just you can say so. OK, but sometimes, in fact, today I'm going to talk a little bit more carefully about like actual running times. We'll care about the difference between quadratic time and linear time and cubic time. And in life, you eventually do care about such things. And in fact, for graph problems, it's customary not to measure the running time as a function of the number of bits in the input. Other things being equal, like you measure the running time in an algorithm typically in terms of the number of bits and the representation of the input. But for graph problems, people are like, no, let's not do that. We usually measure runtime in terms of two parameters. Which are usually n, which is the number of vertices, and m, which is the number of edges. OK, so you might like often see something like a running time. The running time for this graph algorithm is order mn. Now, one thing to say is, first of all, because that's quite helpful to know, we always have that the number of vertices is at most n squared. Sorry, the number of edges is at most n squared. So if you have a running time that depends on m, you could always replace it by n if you want. So this would be order n cubed. And furthermore, the size of the representation of the graph is pretty much always order n squared. Even in the adjacency matrix format, it's like order n squared. And it's at least, kind of order n. You have to at least, write down the name of, for each vertex, you have at least to say something about what its neighbors are. So all of which is to say that like all of these quantities, the number of edges m and the representation size of the graph, they're all polynomially related to n. So again, if you just care about whether a problem is in P or not, then any algorithm that looks in polynomial time as a function of m or as n or the actual size of the input, it's all the same. OK, so if you care about putting problems in P, then that's fine. It justifies that it's OK to look at polynomial running times in terms of m and n. And that's what people usually do. That's somehow the most interesting way to parameterize graph problems, runtimes, in terms of the number of vertices and edges. Any questions about this? OK, so now I'm going to talk about solving this problem path. Well, as I said before, it's actually like the problem of like solving a maze. Like if you're given like a maze, like such as kids play with, it's basically a graph, and you're trying to get from the start to the end. So if you're not too sophisticated, it could seem like a hard problem. And in fact, there's a brute force solution, which is the first thing that could occur to you. I mean, given the definition of the problem. A candidate solution, or in fact, a solution looks like this. It's, to find a path, for example, it looks like a list of vertices, v0, v1, up to vl, where the first one is s, the last one is t. And where vi plus 1 is an edge for all I. Okay, that's what you're looking for. A sequence of vertices, each two adjacent ones form an edge. The first one is s, the last one is t. You're trying to figure out if that's in the graph. And I mean, some good news for you. Any solution it's not going to be like arbitrarily long. Okay? We can say without loss of generality, the number of vertices in the path that you're potentially looking for is at most what? What is it? N, yeah. There's no reason to have a path that's like way longer than n because there are only n vertices. If you visit a vertex twice, like you don't have to do that. Like if you visit a vertex, do some stuff, come back to the vertex, and then get the t, just like cut out that part where you started at a vertex and came back to yourself. So, okay. So the number of candidate paths is at most, well, basically there are n possible vertices along the path, and each one is a vertex, so there's at most n of them. So it's at most n to the n. Okay, which is 2 to the n log n. So there are at most exponentially many paths. And to check a path, it's not that bad, right? I mean, if somebody writes down a list to you of at most n vertices, and you want to check that it's really a path, well, you just have to like go through the n vertices on it and really check this condition that each one really is an edge. And we're going to assume like a normal pseudocode that if you have the names of two vertices and you want to check if that's an edge, you can do it in constant time. Let's assume we have the adjacency matrix. And so we just have to look at this entry in this two-dimensional array. We'll say that takes order 1 time. It's not a big deal. So you can check a path. If a candidate path is really a path from S to T in order n time. OK, so we can solve this problem with brute force in time, maybe order n times n to the n. OK, so therefore, this path is in P, is in X. Well, that's an example of what I mean by how there's like a brute force solution that can solve the problem for you. But as I hope you know, you can do a lot better than this. There's a smarter algorithm that will solve it in polynomial time. Does anybody know the name of one algorithm that will solve this in polynomial time? Yeah? Yeah, breadth-first search is an example of an algorithm that can actually solve this in polynomial time. Do a breadth-first search starting from S and see if you hit T. Saw that in 251, among probably other places. In fact, I'm not even going to write that. Let me even write a more naive algorithm, just for fun. This is the one that like Sipser writes, for example. It's naive, but also smarter, a lot smarter than this. So it's going to show it's in polynomial time. So here's a naive algorithm. And I write this as like an example of like pseudocode, the pseudocode that we're going to eventually write when we're talking about solving algorithms problems. We're not going to like talk much more about Turing machines. So you should first mark S. And that means as reachable from S. That's what the marked vertices are going to mean. OK, and then we'll do a loop. And just, this is a very naive algorithm. Go through all the edges. UV. And if U is marked, and V is not, then mark V. OK, and keep going for a while. Actually, you keep repeating this until no new vertices are marked. So this is actually also a loop, really. You're going through all the edges, and you're starting to mark potentially more vertices. You keep track of how many vertices you marked on this pass through. And if it was 0, that's when you stop the loop, the big loop. And I claim, and I'm not going to prove it, I hope you see it, that like actually when you finish this, the set of marked vertices is the set of all vertices that can be reached from S in the graph. So therefore, you accept, or say yes, if T is marked. And reject otherwise. OK, so this is not the best algorithm for the ST path problem, but it's a fine algorithm. As I said, this is an example of like pseudocode written algorithm. And when you design an algorithm, you should, of course, first prove that it's correct. I'm not going to prove it. But yes, it's correct. OK? So I mean, as I said, the set of vertices that end up getting marked is eventually all the vertices that S can reach. And let's do the time analysis. Well, this first step we consider to be, let's say, constant time. Now, we'll come back to how many times this loop could be iterated. But this stuff inside the loop, go through all edges. Well, that takes like order m time, right? Proceed through all the edges. And this is some constant time stuff. And what's an upper bound on the time or on the number of times this loop will get repeated? Yeah, O of n. In fact, it's n even, because every time this loop repeats, you mark at least one more vertex. So it can repeat at most n times. OK, so this time is at most order m times n. OK. And that shows that this path problem is in P. Because this is a polynomial running time. If you want, this is at most order n cubed, which is, if you really, really want, it's like the size of the representation of G cubed at most. So this is the worst case, maybe cubic time. Great. That's it. So we showed the problem that, maybe at first naively it looked like you might need exponential time, but we showed that it's in polynomial time. OK, so it's not really an algorithms class. So on one hand, I would say, well, we can just leave it at that. It's in polynomial time. But it's a little bit galling for such a basic problem to leave up there this somewhat inefficient algorithm. So I'm not going to remind you of how breadth-first search works. You saw it in 251. But let me just say that you can do it faster with breadth-first search. And here's some example. I'm not even going to write proper pseudocode for breadth-first search, although it doesn't take that long. But I'm just not going to do it. But let me remind you how breadth-first search kind of works. In a graph, let's say this is S. It's got some neighbors, A, B, C. And maybe they have some relationships between them, like, I don't know. And then this has some D. I don't know, something like this. So breadth-first search, basically the way it works is it marks S, and then it marks all the neighbors of S. Let's NBRS is neighbors for me. So it marks S, and then it's at S, and it looks at all the neighbors. There are 3 here, so it marks them. And then it marks their neighbors. In particular, it marks their unmarked neighbors. OK, and then it marks their unmarked neighbors. OK, and so forth. So this is too much. This is not really proper pseudocode. But as I said, I'm not going to write breadth-first search pseudocode out. But this is the idea of it, right? So it goes from S, then it marks all A, B, and C. And then it goes through the ones that are sort of on the frontier, like A. It looks at all its neighbors. One of those is S, but it's like, never mind, I already marked that. So I can mark D. And then B I've already marked, and C I've already marked, and then I'll proceed from D, and it will mark E, and A it's already marked, and it finally marks T. Okay? In order to do this efficiently, you actually use a data structure. You use a data structure called a queue. Which is really just an array where you put things in on one side and take them out at the other side. And if you do this, then this is doable in order m time. Basically, somehow in this breadthfirst search, starting from S, you really don't need to look at any particular edge more than like one time. Okay, and so therefore, the overall running time, if you're a bit careful about how you organize things, is proportional to the number of edges. Okay, so I'll just remind you of that fact that you've seen before. And let me just also add, because I'm bringing this up because it's good to know or remember, if you're even slightly more careful as well when you're doing breadth-first search, you can learn something better than whether just S is connected to T. You can even, while you're doing this, you can compute the distance from S to T, actually from S to U for all U in V in the same amount of time, order m. And distance means the least number of steps you need to get from S to U. And that's just because you basically mark S, instead of marking out everything with a check mark, like mark it with a 0, and then mark on the next step with a 1, and on the next step with a 2, and on the next step with a 3. So you can just say, you can get from S to S in 0 steps. Then A, B, and C all get marked with 1. And the newly marked neighbors on the next step get marked with 2. And then on the next step with 3, and 4, and so forth. OK, and you can imagine that all the ones that never get marked are marked with infinity. Okay, so actually at the end of breadth-first search, which you can do in order m time if you want, you actually know the distance from S to every vertex, or you know that you cannot get to a certain vertex from S. OK. So I want to remind you of that because actually the path problem is very important even in complexity theory. We're going to see it come up again and again. We're going to see, like, for example, later in the class, an algorithm for the path problem that's neither breadth-first search nor depth-first search. It's quite unlike any algorithm possibly you've seen before for solving the path problem. It's like middle-first search. In fact, the path problem is also going to come up again tomorrow or next time when we talk about 2-sat. So it actually plays an important role in complexity theory. So that's why I wanted to spend a little bit of time on it. OK. So that's it. So next I'm going to tell you another actually quite similar problem that you could solve in polynomial time. But from the definition, it looks like you might need exponential time. So this is a problem called two-coloring. Sometimes people just write COL. That stands for coloring. So the input is a graph. And this time it's undirected. OK, and you're supposed to output yes or no. I guess you probably know this problem, but I'll say it anyway. Yes or no. Is there a valid two-coloring? Of G. OK, well, what's a valid two-coloring? That's like a graph theory term. What is it? It's an assignment of either red or green. Now, let me make it blue so it doesn't start with G. Blue to each vertex. This is vertex for me, VTX vertex, such that, ST, no edge has both vertices the same color. Okay. Great. So this is a problem you might want to try to solve. So there's a brute force solution to this problem. That's just inspired by the statement of the problem. Well, there's only so many candidate colorings. I mean, you have to try to find a candidate coloring that is valid in the sense that no edge has the endpoints the same color. How many candidate colorings are there? I know you know this one. How much?
There are 2 to the n.
2 to the n, yeah. There's n vertices. Each one can be red or blue. There's 2 to the n possibilities. And now, if somebody wrote down a candidate coloring and asked you to check if it's valid, how much time would it take you to do that? Order m, yep, that's right. You just go through all the edges and check if the endpoints that have the same color. OK, so you can do this in time. The brute force solution, runtime, order m times 2 to the n. OK, so therefore, 2 coloring is in exp. Great. Well, in fact, you can do it smarter than this. This problem is solvable in polynomial time. Can somebody say an algorithm? I think you may know it one. Yeah. Oh, so it's a hand up or yes?
Pick a coloring and then just keep adding, like the greedy algorithm, just keep adding colors while they don't conflict.
Yeah, it's basically like try the greedy algorithm, and if it doesn't work, say no. And if it does work, say yes. Now, that's risky in general in life to just say that if the greedy algorithm doesn't work, then no algorithm, like no coloring is possible. But in this case, it's possible. Let me just pretend that all the, I don't want to redraw a graph, so let me pretend that all the edges here are undirected edges. So what you do is you just start with any old vertex you want. OK, and it's supposed to either be red or blue. Well, it really doesn't matter, right? I mean, the first vertex, if you have a correct coloring, you can swap red and blue, and it's still a correct coloring. And so therefore, it doesn't matter, like, if you focus on one vertex, what it is. So you can say, let's try red. Or if you really want, you can try both red and blue. You're going to come to the same result. OK, and then this is the reasoning. I'll just say it out loud. I'm not going to write the proof. But if there is a valid 2 coloring, with this being red, then like all its neighbors have to be blue. There's like no other possibility. So like you can just say like this would have to be blue, this would have to be blue, this would have to be blue. Like you haven't made any arbitrary choice here. Like your hand is totally forced. OK, and then you go from these guys. It's exactly like breadth-first search, really. You go from these guys and look at all their neighbors and try to color them red. And if you don't get any conflicts, then great. If you do get any conflicts, you know the graph cannot be 2-colored validly. So actually here, you would be able to stop, because you'd say, well, now I have an edge between blue and blue, which is impossible. OK, and like there's no way to get around that in this graph. Like no matter what you color this has to be the opposite color, this has to be the opposite color, but then these are the same color. So the algorithm is just take any vertex, without loss of generality, color it red. It's exactly like breadth-first search. Color all its neighbors blue. Color all their neighbors red. And if there are conflicts, you can reject immediately. OK, and then color all their neighbors blue. And if conflict, reject. And keep going until you've colored all the neighbors that are connected to the vertex you started with. Actually, technically, you're still not done. What do you have to do after that? Yeah.
And any uncolored vertex inside of it.
Yeah, technically, if the graph is not connected, you still have more to work on. So you have to go to the next connected component and do the same thing. Repeat for all connected components. OK, but basically, if at the very end you colored everything, then you could accept. So as we said, this is a kind of a special problem where if you just, it's easy to reason that if you just try the greedy algorithm or just try what you are forced to do, then you can just check whether or not it's possible. OK, so let me just say that this is a correct algorithm. And again, if you are a little bit careful, it's easy to see it's in polynomial time. If you're a little bit careful and use a Q data structure, you can even do this in time order m plus n. How come it's not just order m, like for breadth-first search? Why did I write m plus n? That's right. It's very rare, I mean, usually in life, but like you can have a graph that has many fewer edges than vertices. Most of the time, like graphs have at least as many edges as vertices, but like technically they may not. And like if you're just trying to check a given vertex S is connected to T, you really only have to explore the edges that are touching S, or connected to S. So it's just order m. But like in this thing, you have to understand a property of the whole graph. So if you like finish like one connected component, you have to go on to all the other connected components. So there's no way to avoid looking at least at each vertex n. OK. Great. So 2 coloring is another problem that's in P. Yeah, we're on a roll. Like everything is in P so far. That's great. Any questions? All right, so let's step it up to the next level. Let's do 3 coloring. So same problem. I'm going to give a graph, find out if there's a valid 3 coloring. An assignment of red or blue or yellow. OK. So this is a new problem, 3 coloring. And well, let's go through this board again. What is the number of candidate colorings? OK, I won't make you say it. It's 3 to the n. Right. Checking if a candidate coloring is valid, order m time. That's still true. So runtime, order m times 3 to the n. It's true. Therefore, I claim that 3 coloring is in exp. Right. Yeah, maybe. Yeah. So, OK. So how about a smarter algorithm? Now, one difficulty is like the algorithm we just saw does not really seemingly work anymore for 3 coloring. Like maybe you might call it the greedy algorithm, because like in 2 coloring, like anytime you try to consider anything, like your hand is sort of forced. But in 3 coloring, it's not the case. So you can still, let's say, without loss of generality, call the first color red. But then, like these 3 don't have to all be blue. They could be blue or yellow. Some of them could be blue. Some of them could be yellow. And it's hard to tell what you should do. I mean, for example, these 2, you should definitely color different colors because they're connected. But that's OK. So you might make this one blue, yellow, and blue. Here, actually, you're sort of forced. But if there are more edges, there'd be more possibilities. And it gets hard. It's like a puzzle. Like now it's not clear what to do. So let me erase this algorithm, since I should have not erased the word smarter, because that's what we're going to care about. So is there a smarter algorithm? Well, we've been very lucky before, so we might ask, is 3 coloring in P? And the answer to this question is it's not known whether or not you can do this problem in polynomial time. It's generally believed that the answer is no. But we don't know how to prove that you cannot do it in polynomial time either. This is exactly the sort of thing that we'll be talking about in coming weeks when we talk about NP completeness and stuff. But let me just say it's not known. So is this the best you can do? Does anybody know if you can do better than 3 to the n? Yeah?
What if you try to make a valid 2 coloring, and then every time you got into a conflict, you could change one of the vertices to a yellow?
Maybe. Actually, I'm going to cut you off because it's on the homework. Actually, you can do this in about 2 to the n time. Well, that's on the homework. The next homework that's coming out. You can do it in time 2 to the n, let's say times poly n. And actually, that's way better. Like 2 to the n is actually way smaller than 3 to the n. That's pretty good. It's not obvious. So maybe you can do it in 1.9 to the n time. Actually, you can. You can also do it in 1.8 to the n time. In fact, in 2005, Beagle and Epstein proved that you can do it in time, well, about 1.33 to the n time. Well, indeed, order this much time. That's very non-obvious. So it's not polynomial time. It's, in fact, still exponential time. But on the other hand, it's much faster than brute force. So it's a funny situation. You can do better than brute force. So maybe if you're very optimistic, you might think, like, maybe there's just like a really awesome way you can get it all the way down to polynomial time. Most people don't think so, but maybe. I don't know. Well, I don't think so. But on the other hand, it just does show that, like, you know, even if it's exponential time, you can do things that are better than brute force. Any questions? OK. Well, all right. I'm going to tell you another problem now that I wanted to tell you about it now because it's an interesting problem. It illustrates another technique for putting problems in polynomial time. And it's kind of in the news lately in complexity theory. Hopefully later in the class, I'll tell you some interesting things about this problem from the point of view of complexity theory. OK, so what is this problem? It's called longest common subsequence. Or LCS for short. OK, so what is the input to this problem? It's 2 strings. X and Y. And let me say they're strings. And let's say they're both of length n. They don't actually have to be the same length. It's perfectly fine if they're not. But like just for simplicity, let's assume that they're the same length. So they're both of length n. So really, the input length is of size 2n. But I'll just call it n. So you have 2 strings of length n. And what do you want to output? Well, it's right there in the title. You want to output the longest common subsequence. I'll give an example in a second. Let me just emphasize that there's a difference between substring and subsequence. Substring means the letters have to be consecutively appearing. Subsequence just means they have to appear in that order, but not necessarily consecutively. And let me, for simplicity, make the task a little bit easier for you. Let's say you just have to output the length of the longest common subsequence. Okay, so you're just trying to find the length of the longest subsequence in common. I'll give you an example in a second. As you'll see, when we eventually solve this problem in polynomial time, once we get the length, it will also be easy to extract the actual common subsequence itself. But let's focus for now on the length of the longest common subsequence. And let me remark also that this is a function problem. It's not a decision problem. So the answer here is not yes, no. The output is supposed to be an answer. It's actually a function problem because there's one correct answer that you have to get, the length of the longest common subsequence. Actually, if I just asked you for the longest common subsequence, it wouldn't be a function problem anymore, because there could be more than one subsequence common to both strings, which are both equally long. So we'll say that. OK. I shouldn't talk about it so much without giving an example. So here's the example. Here are two inputs. X could be the string algorithm. And y could be the string atavistic. That's a word. OK. So what is the length of the longest common subsequence of these two strings? Can somebody find out? What's the answer? Is it 8? No? Smaller than 8? Bigger than 1? Yes? 2. I think it's bigger than 2. Yeah. Let's see. It's 3. So how can you draw a solution? Basically, the way I like to draw a solution, I hope this is a different color, but it's not. Oh, well. This is terrible. Oh, my God. You just draw a line between the matching characters. OK, so these 3 lines, it's very hard to see in my drawing, sorry, are like saying this A and this A kind of match, this I and this I match, this T and this T match. OK, so the longest common subsequence is AIT. And it appears like AIT, AIT. See, it doesn't have to be consecutive. So the answer for this example is 3. Well, you have to check that you cannot do 4, but I think you cannot do 4. OK, so this is a problem that actually comes up in, like, I'm told, like biology, like if you have sequences of A's, C's, G's, and T's, for some biology reason, you care about like the length of the longest common subsequence. If you're trying to compare 2 strands of DNA and see if they're like similar or something. So if they have a really long common subsequence, then they're similar. OK. Well, let's do what we always have been doing. Let's first consider brute force solution. OK. OK, so the number of subsequences, let's say, of x is how many? Can somebody say it out loud? Not n squared. 2 to the n, yes. It has 2 to the n subsequences. Basically, you can choose any subset of letters of x, and that is a subsequence. OK, and then you can go through all of those. And to check if a subsequence appears in y of x is in y, if I give you a subsequence like a, v, s, and I'm like, does this appear in y? You can do that in order n time. You make a linear pass. It's not hard. Great. So the whole thing is in order n 2 to the n time. So therefore, I cannot say it's in exp, because exp is a collection of decision problems. And this is not a decision problem. So it's a technicality. But anyway, you can say it's in exponential time. You can solve it in exponential time. OK, but there's a smarter way to do it. So I'll tell you a smarter way to do it. And the smarter way relies on an observation. Let's say you're given x and y. If they have the same first character, you may as well take it. Let me not say a precise definition of what I mean, but I think you'll get the point. If you look at your 2 strings, and this is like an example, They have the same first character. Now you could say, well, maybe I can make it even longer common subsequence if I don't match these two characters. But that's not the case. If you can match the first two characters, you may as well already do it. You see, we didn't do it here, but if neither A was matched to anything in the longest common subsequence, well, it wouldn't be longest, because I could also match the A's and gain one more. And in fact, even if the A is matched to something in the longest common subsequence, like in this case, I can always match it to this A, and it doesn't hurt. So I can take this line and do this instead. Okay, so it can never hurt to match the first characters, if they do match, to say I'm going to match them, and then just process the two suffixes. So that actually leads to a recursion, actually. So let me write LCS for the length of the longest common subsequence of two strings. And from this observation, you can tell that it's 1 plus the length of the longest common subsequence of the suffixes if they have the same first character. And if they don't have the same first character, well, then you can either ignore the first character of x or ignore the first character of y. So what I'm trying to say is it's either the max of the LCS of x 2 through n and y1 through n, or x1 through n and y2 through n. Closing the max if they have different characters at the beginning. Okay, do people agree with this? Even if you don't, it's not an algorithms class. I'm not going to insist that you get all the details here, but I think it's a straightforward observation. And this actually suggests a recursive algorithm for trying to find the length of the longest common subsequence. Because you see you're making progress here when you do this. The strings that you're sort of processing are always suffixes, so they're always getting shorter. So from this observation, you could get a recursive solution. And then how much time does it take? You'd have to write down a little recursion and solve it. Does anybody know what you would get? Something like it of two parameters would be like t of n, m, or t of a, b. It's maybe 1 plus t of a minus 1, b minus 1 in one case. The trouble is, if all the letters between x and y are different, you might always hit this case. Maybe x and y have no letters in common, then you'd always hit this case. So I'll let you solve it if you want for fun. It's actually terrible. It's horrible. This would lead to an algorithm. It has an exponential solution with, at most, I think, 4 to the n recursive calls. That's terrible. That's another exponential time algorithm. But there's something bizarre about this. I mean, it's a good start. There's something bizarre about the fact that this is, could make exponentially many recursive calls, which is the following. Every time you make a recursive call, you're doing it on some suffix of x and some suffix of y. So every subproblem here, is a suffix of x and a suffix of y. How many suffixes of x are there? N. Or maybe n plus 1, depending on how you count. But let's say n. And there's n suffixes of y. So they're only n squared, different subproblems to solve. So if you just naively implement this algorithm, it could make like 4 to the n, basically 4 to the n recursive calls. But like there are only n squared different problems that it's ever trying to solve. So it's calling like the same problem like over and over again, like exponentially many times. So what should you do? Yeah, there's a technique called memoization. So just if you solve a subproblem, just remember that. Like put it in a box and say, hey, I got the answer for this. And then if you come to a recursive call where like you're about to like try to solve a subproblem, just check if you already solved it. And if you did, then don't resolve it. You have the answer. So that's called memoization. It's also basically the same thing as dynamic programming, which I hope you've heard of. So these techniques like memoization and dynamic programming are important general techniques for showing problems that are in P. So in the end, if you think about it for a little bit of time, you really don't need to even use recursion. Basically, these techniques lead you to the following idea. You can just build a table. Try to like fill out a two-dimensional array, an n by n table. I'll call it table. Let's say ij, where the entry in the ij position is supposed to be the longest common subsequence of the suffix of x starting from the ith position and the suffix of y starting from the jth position. So like your goal in the algorithm for this problem is to fill in all the entries of this table. Actually, you really only care about the top left entry, the 1, 1 entry, because that's the answer, the longest common subsequence of all of x and all of y. But the point is, if you think about it, to figure out an entry in this table, based on this recursion, you only need to look at entries that are like below and to the right. I'll draw a picture in a second. And so therefore, you can like fill in this table sort of directly from the bottom right all the way up to the top left and get your answer. And the running time will be proportional to the size of the table, which is n squared. So I'm not going to write the pseudocode, but I'll draw a picture to illustrate the point. So I'm going to do it on 2 specific strings, but not those ones because I cannot draw a table that large. Let's say x is the word rare, and y is the word area. I think the answer here is 3, if I'm not mistaken. So you're building this like table, and it's going to be n by n, which is 4 by 4. Let me draw it. And let me actually write the words up here, because that will help. And as I said, we're going to build it from the bottom right to the top left. So in this entry, I'm supposed to look at what is the longest common subsequence of this suffix, which is the letter E, and this suffix, which is the letter A. Well, if you have 2 one-letter strings, it's just 0 or 1, depending on whether they're the same or not. And they're not the same, so I'll write 0. OK, and now I can actually solve anything that's like up or to the left of what I've already done recursively. So let's say I go to this thing, this entry. That's supposed to be the length of the longest common subsequence of this suffix, EA, and this suffix, E. So what I do here is I first check if the 2 strings I'm caring about, EA and E, start with the same letter. And they do. So in that case, I know that I can take that letter and pay 1. And then I just have to figure out the longest common subsequence of, well, really the empty string and A, which is 0. So maybe you can imagine there's zeros outside this table. Anyway, this will be like a 1. And this one, similarly, it's the longest increasing common subsequence of RE and A. Let me just say it's 0. Let me imagine this entry now. It's the longest common subsequence of RE and EA. They don't start with the same character. So like in this definition, like the first row is not the case. But the recursion says like it's either the max of this entry or this entry. So you can, to fill in this table, you first check if they have the same letter. If they are, you do 1 plus this guy. And if they don't have the same letter, you do the max of these 2 guys. So you're like, not the same letter. It's the max of these 2 guys, so it's 1. And then these guys actually have the same letter, so it's 1. These ones don't, so it's 1. Anyway, I'm just going to read off my paper now. 2, 2, 1, 1, 1, 2, 3. Okay, let me just do the last one, like the critical final step. Again, it's the longest common subsequence of the whole strings now. What you just say, is this letter the same as this? No. If it was, you'd do 1 plus this guy. If it's not the same, you do the max of this and this. And so it's 3. OK, and that's like the end. That's the answer. So you just illustrate this to say that like you can do this whole algorithm in order n squared time. Because to fill in a table entry, you just have to check if the letters are the same. In that case, you do 1 plus this guy. Otherwise, you do the max of these two guys. So you do a constant amount of work per table entry. And finally, let me just add, well, actually, any questions about this? I went a little bit fast, but maybe you've even seen it before. Let me just add, actually, once you have this, it's also easy to figure out the actual substring that achieves the maximum. It's actually a bit like the path problem. You like start here and like, well, I'll let you think about it, but like you can imagine somehow this path from here to here lets you figure out what the actual longest common subsequence is. Well, just think about it. It's not hard to figure it out. OK, as I said, I'm going to go on to one last problem now. But one reason I brought up this problem is great. We did it in order n squared time. People really do this, I guess, on biological data that has like millions and millions of letters, billions of letters. So n squared is actually pretty slow. So it's p, but polynomial time. So can you do it in order n time? Can you do it in order n to the 1.9 time? So people really care about the answers to these questions. And the answer to both questions is we don't know. But this is also the realm of complexity theory. Like, perhaps you believe that the answer to this question is no. So that's something you could strive to prove. Maybe that there is no n to the 1.9 time algorithm for this problem. And we'll see later in the class that people have proved something like that, assuming not p versus np, but something different. This is a little taste of something that is to come. In other words, there are complexity questions even once you have a problem in p. You still want to find faster algorithms for it. And this is the realm of complexity too. OK, so let me talk about one more problem. It's not going to be like a really amazing punchline or anything. It's just one more problem, and then we'll be done for today. It's called the 3-clique problem, or also known as triangle finding. OK, so the input to this is a graph. I'm just going to stop writing the encoding notation. It's an undirected graph. And now it's a decision problem again. It's a yes, no answer. Yes or no. Does it contain 3 vertices? So u, v, and w with all possible edges between them. OK, so basically you're just looking you're trying to look in the graph to see if it has a copy of this anywhere. And that's why it's called triangle finding. OK, so that's the problem. So let's do what we always do. Let's see the brute force solution. So what's the running time of the brute force solution? Yes?
N choose 3.
Yeah, n choose 3, like order n cubed. I tried to trick you. The brute force solution is already polynomial time here. It's not exponentially many. I mean, you can just do the obvious thing, just like enumerate all 3 different vertices. There's n, choose 3 choices for that. So let's at most n cubed. And then just check if all 3 of the associated edges are present. That's order 1 time. That's it. Brute force time, order n cubed. So it's in P. Great. OK. Well, we can still ask, though, this. I mean, just like this. Great, we got it in P, but maybe we want to try to get it even better. So what about a smarter solution? For example, can you do it in, what do I want to say here? Order n squared time. Let me let you think about it.
Once again, with the greedy algorithm of if three edges form a triangle, consider it a triangle, and maybe that gets the most.
Sorry, what is the algorithm exactly? Like,
Or just vertices that are next to each other and try to see if you can just like go too deep.
yeah, so let's see. You can go. OK, you can go through all maybe. You can go through all the edges. Let's say. So you go through all the edges. So that's like order m time. Now, for each edge, basically you're trying to figure out, is there some other vertex that's connected to both of them? Which is actually order n time. So actually, this gives you order m times n. Yeah. So actually, that's better. In some ways, that's better. I mean, if you're allowing yourself to depend on m and n, that's potentially better than n cubed, like for a sparse graph, let's say. But let's say, OK, that's a good point. Actually, for this problem, let's only worry about running time as a function of n, because somehow the point I'm trying to make involves that. So you could say that this is, in the worst case, if there's many edges, there could be as many as n squared edges. This would be order n cubed.
Find a triangle.
It's true, actually. It seems like if there are many edges, you have a better chance of finding a triangle very early. Of course, if they're all n choose 2 edges, then you could like check that in quadratic time, and then there's definitely a triangle. So maybe the harder case is, what if there's like 0.1 times n squared edges? Yeah?
Maybe try something involving a modified breadthfirst search and see maybe if you can, for a given node, find itself in its third neighborhood.
Yeah, I mean, let's see.
Basically, when you're extending the frontier, also look at the grandparent node and see if it's in the frontier.
Yeah, the trouble is, like with breadthfirst search, like you kind of, if you see an edge that goes back, you generally like ignore it. You kind of like forget about its existence.
Maybe do it so that you only watch that when you're expanding the frontier just the second time.
Well, no, because you could
Oh.
you want to try for all triangles. You would want it throughout the entire graph.
Yeah, I mean, it's not obvious. It's a good question. You guys you should really think about it. So I'll tell you. The answer to this question is it's unknown. But actually, this is a particularly interesting question where I would not say there is a consensus on whether it's possible or not. I think, like, a lot of these problems, these things I talk about, they're unknown, but people pretty much kind of have a feeling on what way it's going to go. Like, for example, pretty much feel that 3 coloring cannot be done in polynomial time. Pretty much, actually, people do feel that longest common subspecies cannot be done in n to the 1.9 time. Whether you can find a triangle in a graph in quadratic time, I think people genuinely, they're like 50-50. I don't know. So it's worth thinking about. It's possible you can even do it in less than n squared time. I mean, as far as we know, you can do it in, I don't know, n log n time. But I don't think people believe that. But just like with this problem, I mean, OK, so you could try to get evidence for whether it's possible or not. Let me tell you this. Here's a fact. You can do it in Well, you can do it in order n cubed over log squared time. That's proven by a former CMU grad recently, by some kind of combinatorial algorithm. I mean, maybe not so different from the things that you've been, trying to think about, which is why I think, it's worth you trying to think about it. Now, in fact, you can also do it in order n to the 2.37, let's say n to the 3.8 time. Actually, the same former CMU PhD student, she had a hand in that as well. Which is pretty crazy, actually. So this one is somehow not a combinatorial algorithm, which is weird. It uses, let's say, algebra. But it shows, again, that you can do something smarter than brute force. So this is kind of amazing. And the fact that you can get it down to n to the 2.38 is, that's such a strange number. People think, well, maybe you can get it down lower even than that. Yeah. Well, that's a crazy fact. But we're going to talk about related problems and trying to understand. So for example, it could well be that the answer to this question is no. And if that were the case, it would be cool, because this would be like a truly natural problem that you can solve in cubic time, but not in quadratic time in that case. And that would be pretty cool. Actually, let me say a few things about a generalization of this problem. So how about the fork-leak problem? It's no longer called triangle finding, so let me ignore that. OK, so the fork-leak problem is you're given an undirected graph. You're trying to find yes or no. Does it contain 4 vertices, x, such that all the edges between them are present? So basically, you're looking for a copy of this in the graph. So this problem, if you use the brute force solution, you can solve it in order n to the 4th time. You just enumerate over all quadruples of vertices, u, v, w, x, and check if the associated 6 edges are present, which is order 1 time. So fork-leak is in time n to the 4th. Is it in time n cubed? We don't know. Is it in time n squared? We don't know. Yeah?
When you switch notation, these capital letters time, I thought that was reserved for Turing machine, though.
Yeah, it's horrible typography. So the following things are all bad. Complexity classes are always written in all capital letters. That's like a fact. And sometimes people even use like a different font, like boldface, or like I personally like sans serif. And this is a complexity class, so like I can't do it on the board, but that's what it is. People also usually write languages or decision problems with all capital letters, like L or fork-leak. This I kind of hate, so I may even stop doing it, but people do it. So that's why I also wrote this in capital letters. But you cannot distinguish like special font in capital letters, plus there's capital letters on the board. Maybe I'll start. But anyway, this is a language, so that's why it's written in capital letters. Yeah, so this we don't know. Actually, for this problem, we don't know any problem that's faster than n to the 4th. Oh, we know n to the 4th over log cubed n. And like 5-clique, similarly, that's in time n to the 5. But we don't know anything better. 6-clique, it's in time n to the 6. Actually, we do know something better. It's also in time n to the 4 point something, 4.7. Okay, so these are some crazy facts. It just goes to show that, like, some problems that are in polynomial time, they could still be very interesting and mysterious. So let me just end by mentioning one problem that's very famous in complexity theory. It's called K-clique. And this is the problem where you're just given a graph G and a number K. And you want to know yes or no, is there a clique of size K? That is to say, K vertices where all K choose 2 edges are present. And this one you can do with brute force in time, well, roughly n choose k for the k vertices times, then you have to check whether k choose 2 edges are present, okay, which is basically like order n to the k, which is good, but but k could be maybe n over 2 or something, and then this is exponential. So in general, k-clique is in X, and we don't know if it's in P. And actually, we believe that it's not in P. Yep.
So is that right, that 6-clique is in n to the 4.7? Because that would imply 5-clique is in n to the 4.7.
Yeah, I thought about that, and then I was like going to check whether that was true or not, and then I didn't. But I'm not 100% sure. Does it immediately apply that?
Yeah, just add a vertex connected to everything.
Yeah, that's what I thought. But then check if there's a 6-clique.
If there's a 6-clique in that, then there's a 5-clique in the original. Because either there's a 6-clique not using your new vertex, which contains a 5-clique, or there's a 6-clique using your new vertex, take it away, it's still a 5-clique.
Yeah, I think he's right. Is he wrong? I think so. OK, so great. So then these are also in. So this one is also in time n to the 4.7 then. Thank you. OK, and so now later we're going to start studying NP completeness, and we'll see these facts that actually you should probably know from 251 that, like, for example, k-clique is in P if and only if 3 coloring is in P. OK, see you next week.